Okay, so for those of you that came to class during exam week, thank you. For the roughly 85% who did not, I'll get over it eventually, so hope you do well in your exams. All right, so let's get into today, and we're going to start with, I guess it's appropriate with 85% of this class skipping to talk about our effort in the course. All right, so what we're going to look at today is how our homework attempts have been trending. So I started on day one of this class emphasizing to all of you that the number one way to prepare yourself for the exams is to do all 4 homework attempts every week. And as you can see from this plot here, things have sort of dropped off as the semester has gone on. I mean, this is not abnormal, but it's something we should ideally try to turn around in the last 4 weeks. So what we'll notice is our effort sort of peaked in week 2 on that homework assignment, and then it's kind of came down a little bit. And then after exam 1, for whatever reason, the number of homework attempts people were doing dropped off a lot. Now, this scale is pretty condensed, so this isn't like a huge difference in number of attempts. This is basically the number of homework attempts per person in this class is what I'm plotting here as a function of each week in the course we've had so far. So there was a significant drop-off after exam 1, roughly about a 10% or so decrease. We've rebounded a little bit after spring break. This is that last data point for just the most recent assignment. But we're doing roughly, 7 to 10% fewer homework attempts now than we were at the beginning of the semester, and typically we haven't gotten the results yet, but typically the second exam has an average score that's about 7 to 10% less than the first. Now, I don't know if those two things are that closely related, but there's something to that, I think. It's maybe not the only and most important reason, but the scores out in exam 2 do tend to be lower, and I think part of that is because people have been doing less homework attempts. I know the semester gets busier, you have a lot of other classes, I certainly understand that, but we talked at the beginning about how doing all 4 homework attempts every week was sort of the key to doing well in this class, or one of the main keys anyway, and I think only maybe about half of you are doing that, so we'd like to see that turn around. There's still, even after this week, there's still 2 more exams, the third midterm and the final, so a lot of chance for you to improve your grade, but that's going to have to come with a significant increase in effort for a lot of you who are not quite happy with how your scores are right now. All right, so we'll leave that behind and go into the material for today. So we're going to finish a little bit with calorimetry. There was one example problem at the end of last time that I didn't get to, and I put that in the notes, but I'm not going to cover it today. So if you want to look at that, you can go back to the posted notes from last week and see if you can do that problem yourself or just see how I solved it. It's pretty much exactly the same as the previous example I did that I ended last week with, so there's not really anything new there. So we're going to move on to newer stuff. And the last thing we're going to talk about with calorimetry is what's called constant volume calorimetry, or the apparatus is sometimes called a bomb calorimeter, which is kind of a violent name, but basically it's a calorimeter that is completely sealed, so it doesn't have doesn't have a vent. It basically, the volume doesn't expand or change, and it's a totally enclosed system. Now, there are some advantages to this type of calorimeter. So, as we'll see, the math that we're going to do for these types of calorimetry problems is pretty much identical to what I already introduced. So it's not really anything terribly new for you guys, but just from sort of a experimental standpoint, there are some key differences. And so the advantages of a constant volume calorimeter, so basically it's an enclosed container, and sometimes it's an enclosed container inside of another enclosed container as it's showing here. You have a small container where the reaction is happening, a larger container that sort of serves as the insulation from the rest of the surroundings, and sometimes some thermocouples and temperature and thermometers to either heat the reaction and monitor the temperature, which of course is important. Now, there are some advantages of this. So first is that it can be used with gases. So these types of calorimeters are especially common for studying combustion reactions. So we want to figure out, how much energy is released when something burns, and that's going to produce carbon dioxide and water vapor as a product. So you need to be able to enclose those gases. If you just have a constant pressure calorimeter, those gases are going to just go everywhere, and it's not going to be very easy to measure the heat associated with that reaction. These kinds of calorimeters are used to determine the calorie content in food. So if you read the back of a food label and it says this has 150 calories, well, this is how they determine that. They use a calorimeter like this, they burn the food essentially and figure out how much energy is released. That's how they measure the calorie content in food. So it's good for combustion reactions especially. Now, technically speaking, it doesn't measure delta H, it measures delta E. We'll get into the math for that here in a second. Now, The reality, though, is, as we said, delta H and delta E are typically very similar to each other, so still, in this case, they're used interchangeably. So you'll often see, measure the enthalpy change in this constant volume calorimeter. It doesn't, don't get too hung up on that. You're technically measuring delta E in a constant volume calorimeter, but delta E and delta H are usually used interchangeably, and we don't need to really worry about that distinction. And the other advantage of a constant volume calorimeter is that because it's completely enclosed, it doesn't release any of its heat to the surroundings, or not nearly as much as a vented calorimeter does. You can know the heat capacity of the calorimeter much more precisely. All right, it's a more accurate apparatus, essentially. So those are some advantages of it, but again, that just mostly comes into play from an experimental standpoint, doesn't really affect things too much in this course. But again, the equations associated with this are going to be very similar to what we talked about last time. The only difference is that, remember that delta E is defined as Q plus W, and we can rewrite W, as we talked about in many situations, as P minus P delta V. That's what when we have expansion work. And when you have a constant volume calorimeter, as the name suggests, the volume of that is constant, so delta V is going to be 0. So in a constant volume calorimeter, delta V has to be equal 0, which means that whole term, minus P delta V, is also 0. So what you can say then is if you measure the heat at constant volume, that's equal directly to delta E. So again, this whole term drops out when your volume is constant. So that's where, as I already mentioned, if you measure the heat in a constant volume calorimeter, Q sub V, that's going to be directly equal to delta E. But for our standpoint, again, the mathematics associated with these types of problems is going to be pretty much identical. The negative heat of our reaction is equal to the heat of the calorimeter. So basically, whatever heat is absorbed or released by the calorimeter is equal and opposite in sign to the heat that's produced or absorbed by the reaction. And that's just going to be equal to the mass of water in the calorimeter, heat capacity of water, and delta T, plus the overall heat capacity of the calorimeter times delta T. And as we talked about last time, depending on the context of the problem, you'll either use both of these terms in your calculation or very often just one of those two. For constant volume calorimetry, it's more common to either use both of them or just use the last one, just group everything together. But nonetheless, you just have to look at what information is in the problem to figure out how do you calculate heat for the calorimeter, and then you're going to relate that to the heat and the delta H for that reaction. Okay, so again, from our standpoint, it doesn't really change things very much. So let's do a typical constant volume calorimetry problem. Again, as we said, these are useful for doing combustion reactions. So imagine we take octane, which is one of the major components of gasoline. We have 3.45 grams of it, and we burn it in a constant volume calorimeter that has a heat capacity of 9.121 kilojoules per Kelvin, or per degree Celsius. If the temperature of the calorimeter rises 17.7 degrees Celsius, what is the combustion enthalpy of octane in kilojoules per mole? Okay, so again, we're looking for enthalpy here, but as we said, delta H and delta E are basically the same, so don't worry about that distinction for these types of problems. So even though we're technically measuring delta E in a constant volume calorimeter, we can still use it to approximate delta H. And then we have a bunch of other information, some of which is going to be, most of which is going to be important for us. So the first thing we want to do is calculate the heat for the calorimeter. So we're telling you that as this reaction happens, the temperature of the calorimeter rises 17.7 degrees Celsius. So this would be an exothermic reaction. It's producing heat, which is getting absorbed by the calorimeter. So that's why the temperature is increasing. So the heat for the calorimeter, as we said, is the mass of the water in the calorimeter, heat capacity of water times delta T, plus the overall heat capacity of the calorimeter times delta T. Now, in this problem here, look closely at the given information. Do we tell you how much water is in the calorimeter? Anybody see it? All right. I don't think it's there, so that's probably why you're still looking. So it's not there in this problem. There's no information about how much water is in the calorimeter. A common mistake that people make is they use the mass of substance in this MC delta T equation. But remember, when we're calculating the heat for a calorimeter, we're calculating how much heat is absorbed by the calorimeter in this case, which would be absorbed by the water in the calorimeter plus any other contents of the calorimeter. So it's only going to be the mass of water that would go into this calculation here, not the mass of the substance you're burning or reacting. So we don't have the mass of water, so basically this is a situation where we don't have to worry about this term, and we're just grouping everything together into one overall heat capacity, which is given there as 9.121 kilojoules per Kelvin or degree Celsius. So this is a situation which is commonly seen in constant volume calorimetry, where we just take all of the contents of the calorimeter, the casing, the thermometer, the water that's inside of it, and we just measure an overall heat capacity for that whole thing, and we just use that. And so in that case then, the heat for the calorimeter is just that constant times the change in temperature, and that's all it is. You don't have to worry about the mass of the water in the calorimeter in this case. So when we do that, we just put those numbers in, so it's going to be 9.121 kilojoules, and again it's per Kelvin or per degree Celsius because it's per delta T, and then we multiply that by delta T, which is given as positive 17.7 degrees Celsius. As the temperature is increasing by that much. So that gives us then a heat of 161.4 kilojoules. Okay? Remember, when we're talking about delta T, the amount that the temperature increases, Celsius and Kelvin are interchangeable because it's just a difference in two temperatures. All right, so we're going to have, that's the heat for the calorimeter. And then remember that what we're looking for here is the combustion enthalpy of this substance, octane, and so we're not quite there yet. So this is how much heat is absorbed by the calorimeter. The heat that is then for the reaction is just going to be the negative of that. So the heat of this reaction is minus 161.4 kilojoules. But again, a common mistake is to stop here, but this is not the enthalpy for the combustion of 1 mole of octane. This is the enthalpy change for the combustion of 3.45 grams. So if you remember that this initial value that we get depends on how much substance we're reacting. So this value here, minus 161.4 kilojoules, that is a delta H value, but this is the delta H if we burn 3.45 grams of octane. What we're looking for is delta H per mole. All right, and this is where we're now going to use the mass of the substance, because the delta H of the combustion reaction per mole is going to be the heat of the reaction divided by the moles of the substance we're burning, C8H20. All right, so we need to take this value and divide it by the moles of substance. So that's going to be the heat, minus 161.4 kilojoules. And now we have to figure out how many moles of that substance we burned and normalize to that. So we use mass to mole calculation, as we've done dozens of times in this course. So we have 3.45 grams of that substance. And we just divide by the molar mass to convert that into moles. 20. And that's going to be given here as 116.24, so we don't have to calculate it. All right, so we get moles of that substance as 0.0297. All right, so we divide the heat of the reaction by the moles of substance to get it per mole. And that gives us minus 5.42 times 10 to the third kilojoules per mole. Kilojoules per mole is the most common unit for reporting enthalpy changes of this type. And that's a pretty big number. So, you know, octane, which is part of gasoline, releases a lot of energy when you burn it, and that's why we use it as gasoline. And it's this many kilojoules per mole, so quite a bit of energy for that. All right, so again, the series of steps are pretty similar, almost identical to what we talked about last time. This was just an example where we didn't tell you how much water is in the calorimeter, so everything's going to be just grouped together into this last term here. And the common mistake, as I said, to watch out for is not using this mass as part of your MC delta T calculation. This is just the mass of substance that we're burning inside of the calorimeter, which is absorbing all that heat. Okay, any questions? All right, yeah.
So the equation basically just telling us to multiply, like, because from what I'm looking at, it's like we could subtract stuff, so how do we multiply?
Subtracting what?
Like, so on the very first line where it says 2 equals that plus CACL delta T.
Yeah.
And then when you said equals, so like, because it's only equals, so how do we know it's multiplying? Because, or is that just the equation?
mean, that's the equation. So you just multiply those two numbers. That's the heat that's the heat capacity for the calorimeter. That's delta T. Those two numbers together give you the heat for the calorimeter, which can be positive or negative. So if it's, depends on if it's endothermic or exothermic reaction. But these two terms, if you have both of them, just need to be added together. It'll be the same delta T for both, and you'll just have to account for the two. I'm not sure if that's what you're
So
asking.
the C Kelvin delta T, that's what's in the parentheses.
Yeah. Yep. So this is your C cal. That's your heat capacity. That's your delta T. And you multiply those two numbers together to get the heat in this case.
Why did the MH20, CH20, and the delta T cancel out?
Because we don't have any information about how much water is in there. So this is a situation where that term, it's not that it's not there, it's just that it's all grouped into that capital C for the calorimeter, the heat capacity of the calorimeter. So we don't explicitly tell you how much water is in there, so you can't account for that. We're just grouping everything together into one term. So there's a few different ways to set these up, and this is one of those where the math ends up being fairly simple because it's just one term. You just have to recognize not to try to use anything for that MC delta T term. All right, I think we're good on that, so let's move on. So what we're going to talk about the rest of today are ways of calculating delta H using known information. So we've covered now calorimetry, which is the experimental method for measuring delta H of a reaction. But often we don't want to have to go in the lab and do an experiment every time we want to measure a delta H. So we can use different ways of doing that where we know something about other reactions and we can sort of use that to find delta H of a new reaction. And that's what we're going to talk about for most of the rest of today. So the first thing we have to introduce to get into that are the idea of consecutive reactions or combining chemical equations, because that's going to come into play for one of the approaches we're going to take to find delta H for a reaction where we don't know what that is ahead of time. So much like mathematical equations, chemical equations can be added and subtracted. So you've probably done, in your algebra courses back in the day, or you'd have systems of equations, 2 or 3 equations you have to solve for your unknowns, and often it involves adding 2 equations or 2 or more equations together. And we can do the same thing for chemical equations. So if we start with a very generic example with just sort of fake reactants and products, so 3A plus 2B going to 4C, let's say that's one equation, and then we're going to combine that with the second chemical equation, 4C plus D going to 3E. So let's say we want to combine these 2 equations. So the first thing we do is just everything on the left side of the arrow gets added together, and then everything on the right side of the arrow gets added together. So the combined equation, if these 2 reactions are happening in sequence, would be 3A plus 2B, those are the reactants from the first equation, plus 4C plus D, those are the reactants from the second equation. So all the reactants just get combined on the left side of the arrow, and the products get combined on the right side of the arrow, 4C plus 3E. So that's how we combine the 2 equations. It's pretty straightforward. And then what we have to do, though, to simplify it is whatever appears on both sides of the arrow will cancel out, because if it appears as a reactant and a product, in net nothing is happening to that substance, so it'll basically cancel out of the equation. So what we see in this equation is that 4C appears on the left and on the right side of the arrow. So when we're combining these 2 equations, that's going to get canceled out, essentially. And so the overall equation would be in standard form written as this. So we get rid of the 4C, and it would just be more simply written in this way. All right, so that species that gets canceled out, that substance that gets canceled out, is what we call an intermediate. So it's something that forms in one reaction and then is consumed as a reactant in the next reaction. So when you're doing, again, a sequence of reactions, an intermediate is something that forms in one reaction and is going to be consumed in a subsequent reaction. All right, and in this example, C would be the intermediate. Whatever C is, this is an intermediate. All right, so substance C forms in the first reaction and is consumed as a reactant in the second reaction, so that would be our intermediate in this case. And because the coefficient was 4 in both cases, then it completely cancels out. Now, in reality, when we're doing this in problems that we'll have in this course, usually the intermediates that are involved are not going to just directly cancel out. They're not going to always have the right coefficients to completely cancel out. So what you would need to do in that case is sort of follow these set of steps here where you're going to have to adjust some of the coefficients. So if we want to combine two or more equations and figure out then the combined equation that results from those, first you have to write out the individual steps, which usually those will be given to you, but sometimes they'll just be described to you. So you have to write out two balanced equations, or however many you're combining. You have to write out balanced equations for all the steps. So let's say the two steps we're considering are H2SO4, so sulfuric acid plus sodium chloride, making HCl and sodium sulfate. Really, we have to do that now? All right, so then we have, that's one of our equations, and then let's say the second equation we're combining that with is, let's say that the HCl that we form in the first step is going to react with iron, Fe, to make iron 3 chloride and hydrogen. All right, so again, we're forming one thing in the first reaction, HCl, which is then reacting in the second reaction to form new products. But what we'll notice here is that the coefficients for HCl are not the same in the two equations. So we're forming 2 moles of HCl here, but then we're reacting 6 moles here. And so if we wanted to add these two equations together, the intermediate HCl would not cancel out. We want that to be the case. So what you have to do is you have to, in some cases, adjust coefficients on one or both of the equations to make sure that intermediates cancel out. All right, so what we'll have to do is make sure that the intermediates cancel. So again, this coefficient here is 2, this one is 6, so we have to triple the coefficients for the first equation. Now to make sure that the first equation remains balanced, we can't just triple the coefficient on HCl, we have to triple all the coefficients. So when we multiply that whole thing by 3, yeah, go ahead, thank you. That helps a little bit. All right, so we're going to triple the coefficients on the first equation. We triple all of them to keep it balanced. And so we'll modify the first equation in this way. It's no longer going to be smallest whole number coefficients anymore, but that's okay because we're just using it to combine with the other one. And so that's how we're going to adjust this first equation. Then we're going to combine the two together. This modified first equation where the coefficients have been tripled, we're going to combine that with the second equation, which we're not doing anything to. So again, the reactants get added together on the left side of the arrow, and the products get added together on the right side. I mean, seriously, they're doing all kinds of work in this building, so if you can hear that if you hear like a buzzing noise on the video, that's what that is. Because I messed up.
What?
Hang on.
That's why I wanted to ask too.
Oh, there should be a 2 there. That's why I didn't write that one right. Thank you. Yeah, so there should have been a coefficient of 2 there that I left out. So when you triple that, it does become 6. Okay, so now we're going to add the reactions together. So in any order. So from this equation here, we have 2Fe plus 6HCl. From the modified equation that we did where we triple the coefficient, we have 3H2SO4 and 6NaCl. And then on the right side of the arrow, we have, from this equation, 2FeCl3, 3H2, and then from this modified equation, we have 6HCl and 3 sodium sulfates. Okay, so that's the whole thing, but again, when we want to write the final form of the equation, we would cancel out the intermediate. So we identified HCl as an intermediate because it's formed in the first reaction, consumed in the second. We adjusted the coefficients, so now both coefficients on HCl are 6, and so then they would completely cancel out from both sides of the arrow. And what that leaves us with then is 2Fe plus 3H2SO4 plus 6 NaCl goes to 2 FeCl3 plus 3 H2 plus 3 Na2SO4. And that would be the final form of this combined equation, where we've adjusted coefficients to make sure the intermediate cancels and then combine them together. And we can see now the coefficients are completely reduced. We don't have to do anything else to that. All right, so any questions on that process? Okay, so then let's go on and just do an example of this. So we have this substance, POCl3, is a common reagent in organic synthesis, and it can be prepared in 2 steps. So the first step, elemental phosphorus, which has a formula P4, and chlorine combined to give PCl5. And the second step, the PCl5, which is our intermediate, reacts with water to produce POCl3 and HCl. So we want to combine the 2 reactions into a single chemical equation. So again, this is one where we're not given the equations, we have to produce them by using the information in the problem. So that's going to be the first step. So we have to get those 2 equations. So we're taking, in step 1, P4 and chlorine, Cl2, to make PCl5. So we have to balance this equation. So if we have 4 phosphoruses over here, we need a coefficient of 4 there. We have 20 chlorines on the right, so we need 10 on the left, Cl2. All right, so that's going to be the balanced first equation. And then we said in the second step, PCl5 is hydrolyzed, meaning that it reacts with water. So water is the reactant in the second step along with PCl5, and those produce POCl3 and HCl. So that's our second equation. We have to make sure it's balanced. So we have 5 chlorines on the left, 3 here, so we need a coefficient of 2 there. 1 oxygen, 2 hydrogens, 2 hydrogens. So that should be the only coefficient we need, is a 2 in front of HCl. So when we want to combine the 2 equations, we need to make sure that the intermediate from the first equation, which is PCl5, is completely consumed in the second. So the coefficients are not the same. So again, we have to adjust one or both of them to make them the same. And we can do that by just multiplying this whole thing by 4 to make sure that PCl5 has a coefficient of 4 again. So we're going to make that to 4 PCl5 plus 4 H2O, 4 POCl3, and 8 HCl. All right, and so then we're going to combine these 2 equations here, the ones that I have stars next to, the first equation and the modified second equation, to make sure that the PCl5 cancels out. And so when we do that, again, that intermediate is gone, 4 PCl5, so I'll just combine those 2 steps into one now. We're going to get rid of that intermediate, and we're going to be left with those 2 reactants from the first equation, P4 plus 10Cl2, 4 H2O from the modified second equation, and then finally we're going to have that product is gone from the first equation. The products that are left from the second equation are 4 POCl3 and 8 HCl. All right, so that's how we would combine those 2 equations into one overall chemical equation that combines the 2 steps into one. All right, so that's just a typical example of that approach. Any questions on that before we move on to the next topic? Now you might be wondering, why does this matter? What does this have to do with delta H? Yeah.
Do we have to check if it's balanced after combining?
If you did everything right, you don't have to check if it's balanced, because it will be. It doesn't hurt to do that, just to make sure you didn't mess anything up. But as long as you multiply everything by the same coefficient like we did in the first case, as long as you add them correctly, the final equation you produce will be balanced by definition. But it never hurts to check, obviously. All right, anything else? Okay, so what we're going to do now is we're going to see, why does this matter for delta H? Because what we're going to end up using this approach for is to find delta H of a new equation where we know the delta H for the 2 equations we're combining. And then by combining those 2 equations, we can also find the delta H for the combined reaction. So in other words, if we knew the delta H for the 2 given equations, for this one here and this one here, we can now find delta H for that combined reaction that blend two of those steps together. So let's see how that works. So to get into that, we have to talk a little bit about the properties of delta H. Okay, so the sign of delta H depends on whether the reaction is exothermic or endothermic. We talked about that before. Delta H can be positive or negative, and that's going to be defined as exothermic or endothermic. So exothermic means delta H is negative, endothermic means it's positive. So that's something we covered a while ago in introducing delta H. So we have two possible signs, and then, how big is delta H? What is the magnitude of delta H? Well, as we talked about a little bit in the calorimetry example earlier, the magnitude of delta H is proportional to the amount of substance that we're reacting. All right, so as an example, if we take water and decompose it into its elements, so if we take 1 mole of water and we decompose it into hydrogen and oxygen, the two elements that make it up, the delta H, the amount of heat that has to go into this for 1 mole of water, is 286 kilojoules. All right, so it takes 286 kilojoules of heat to decompose 1 mole of water into hydrogen and oxygen. All right. And so when we do the reaction where we produce 1 mole of H2 as it's written, the delta H for that is exactly the same, 286 kilojoules. This is called a thermochemical equation. It's an equation with a delta H. This 286 kilojoules is associated with the production of 1 mole of H2 because H2 has a coefficient of 1 in front of it. But let's say we were doubling this and instead we were decomposing water to produce 2 moles of H2. Well, delta H scales directly with the scale of the reaction. So if we do the reaction at a larger scale where 2 moles of H2 are being produced, delta H would be exactly double that. 572 kilojoules. So delta H scales with the delta H scales with the scale of the reaction, which means if we adjust coefficients in a chemical equation, we adjust delta H by the same amount. So again, this would correspond to the equation where we doubled everything, 2H2O going to 2H2 plus O2. So we write the equation that way with whole number coefficients where we're producing 2 moles of H2. Delta H is now doubled because all the coefficients are doubled. So that's how the sort of magnitude of delta H relates to the scale of the reaction. Okay? So then this allows us to understand then what happens if we take a chemical equation and we adjust it in some ways. Because when we're combining chemical equations to find an unknown delta H value, sometimes we have to change something about the reaction. As we saw already, sometimes you have to adjust the coefficients to make sure the intermediates cancel, and then other times you might have to flip the whole direction of the reaction to make sure that the right intermediate is on the right side of the arrow, or the right reactant or product is on the correct side of the arrow. So if we reverse a reaction, then delta H just changes its sign. So if we consider this equation here, the decomposition of magnesium carbonate into magnesium oxide and CO2. This is an endothermic reaction with a delta H of positive 117 kilojoules. But if we remember that delta H is final minus initial, which is products minus reactants, it should be clear then if we switch the whole direction of the chemical reaction, we're going to switch the sign of delta H. So if we swap reactants and products, so now if we consider the reverse reaction where manganese oxide reacts with CO2 to form magnesium carbonate, so if we do that instead, we've switched reactants and products, we basically flipped the whole direction of the reaction, and so now instead of products minus reactants, we just change the sign of that because the products and reactants have been swapped, and that becomes minus 117 kilojoules. So if we just flip the direction of a chemical equation, basically invert the reactants and products with each other, then the delta H just changes sign. That's what we see here. All right. And then as we already sort of talked about in the last example, if we adjust the coefficients of a chemical equation, delta H scales by the same amount that we've adjusted the coefficients by. Okay? So if we take this first equation here, magnesium carbonate going to magnesium oxide and CO2, if we double the coefficients, which again, this is not the standard way to write this, but we might have to do this in some cases to make sure that intermediates cancel and things of that sort. So if we double all the coefficients were 1, we double them to 2, delta H will also double. So it's going to be 2 times the original value. Or if we took this first equation here and we multiply the coefficients by 1/2, so again, not standard to use fractional coefficients, but not wrong to either, and sometimes going to be necessary in these types of problems. So if we multiply all the coefficients by 1/2, we also then multiply delta H by 1/2. Okay, so those are basically the two things we can do when we're combining chemical equations. We can flip the direction of the reaction, which flips the sign of delta H, or we can, in some cases, we'll have to adjust the coefficients, which then multiplies delta H by that same factor. And in many cases, some combination of those two where we flip the sign and adjust the coefficients. So those are the properties of delta H, how it changes if we, change a chemical equation. All right? So that's going to be something that we'll use in the context of what is called Hess's law. And this is telling us then what happens to delta H when we add chemical equations. So when we add two equations together where we know the delta H value, the delta H for the combined equation, that's the sum of those two, is just the sum of the two delta H values. So whenever we're combining equations in the way that we've been describing today, the delta H's for those are additive. All right, so if we give you this thermochemical equation here that we already talked about, where the delta H is 117 kilojoules, and then we want to give you, a second chemical equation that you're going to combine that with. So let's say the CO2 that was reproduced in this reaction is reacted in a second reaction with H2 to make methanol in water. So that should be balanced, and the delta H for this is minus 131 kilojoules. When we combine the two equations, the CO2 cancels out because it's formed in the first equation, reacts in the second, it's an intermediate. And so this overall equation here, where MgCO3 plus 3H2 reacts to form magnesium oxide and methanol in water, the delta H for this overall reaction, the total delta H, is going to be the sum of the two that we added together. So we added those two equations, 1 and 2. We will also add their delta H values. So it's going to be 117 kilojoules plus minus 131 kilojoules, which is minus 14 kilojoules. Okay? So again, if we know the delta H for two equations that we combine, we can find the delta H for the combined equation, which will be in this case minus 14 kilojoules. So that's what Hess's law allows us to do. It allows us to take known delta H values from equations that we combine in this way and allow us to find a delta H for a different reaction that's some combination of those. All right, so that's going to be the concept we're going to use. So any questions on that so far before we dive into the example problems? Yeah.
So if we have to change the scale for one of them to make them match, would we change the delta H and then that?
Yes, so you'll change the individual delta H value for whatever reaction you adjust, and then you'll add them together. And we'll see examples of that in these next few here. So let's see how that works. Anything else? All right, so let's go into 3 examples of varying complexity. So the first one, the simplest one you can have, is where you're combining 2 equations. So the way that these are going to be set up is we're going to give you an equation, in this case the dimerization of NO2 to make N2O4, and we want to know what the delta H is. That's our unknown delta H. And we're going to give you 2 or sometimes more than 2 equations where we know the delta H, and we have to figure out how to combine these 2 equations to get this equation, and then combine the delta H's to get the unknown delta H. So it's going to be a little bit of a puzzle in some cases to figure out how to combine the 2 equations, or sometimes more than 2 equations. But what you want to look for in these is you want to find, okay, let's look at for the overall equation, we need to have two NO2s on the reactant side, we need to have N2O4 on the product side. So look at which of those given equations NO2 appears in. So we see that NO2 appears here in the first given equation as a product though. So this reaction here has one NO2 as the product. What we want is to find an equation where we have two NO2s as a reactant. So to make that work, we are going to flip this first equation to make NO2 a reactant, and we're going to double the coefficients to make the coefficient now 2 in front of NO2. So if we take minus 2 times equation 1, if we call this equation 1 and this equation 2, the two given equations, we're going to flip it and double it. So that's going to move NO2 to the reactant side and put a coefficient of 2 in front of it. And then these two are going to go to the product side with their coefficients doubled. So it's going to be 1 N2 and 2 O2s. And the delta H for this modified equation, because we flipped it and doubled it, it's going to be minus 2 times the first delta H value. All right? Because when we flip an equation, we change the sign of delta H, so it'll go from positive to negative. And then since we double the coefficients, the whole delta H doubles as well. So that gives us the modified delta H for equation 1 after we flipped and doubled it. And then we have to figure out what do we combine this with. So you can either look at intermediates, or what's easier to do, I think, is to again look at what products we need as well. So we have 2 NO2 on the reactant side. We need N2O4 as a product. If we look at the second equation here, N2O4 is already on the product side and already has a coefficient of 1. So that should tell us that we don't have to do anything to equation 2. If we add equation 2 to this modified equation 1, that will give us 1 N2O4 on the product side, which is what we need for the reaction we're trying to find delta H for. So we're going to take equation 2 in an unmodified form. So it's just going to be N2 plus 2O2 going to N2O4, and the delta H doesn't change because it's the same equation, plus 10 kilojoules. And so if we trust ourselves that we did this correctly, now we can just add everything together. And so what we find out is that on the reactant side, we have 2 NO2. From equation 2, we have N2 and 2 O2, but those are going to cancel out with N2 and O2 from the first equation that's on the right side of the arrow. So N2 is an intermediate, which completely cancels out. 2O2 completely cancels out, and all that's left on the product side is going to be the N2O4. So we've successfully added the two equations together to get the equation we're looking for, and now the delta H is just going to be this value here, minus 68 kilojoules, which is the modified delta H for equation 1 after we flipped it and doubled it, plus the second one, which is 10 kilojoules, which comes out to minus 58 kilojoules. All right. So in problems like this, as I said, you want to look at reactants and products in the reaction you're trying to find delta H for, and then you want to find in the given equations where those reactions and products only appear once. If you try to balance it by canceling out N2 and O2, there's going to be infinite numbers of ways you can do that, and so you have to really look closely at the reactants and products that are in the overall equation and figure out from there how to modify and then combine the two given equations. So any questions on that? All right, so let's step it up a notch and go to one with 3 equations. I mean 3 is about as high as we'll make you guys go. I think there's maybe like 1 or 2 problems in the question bank that require you to do more than 3 equations, but they're a little bit more straightforward in some regards. So 3 is about as high as we'll go. So we're going to calculate the enthalpy for this reaction here. We're forming C2H2, which is acetylene from the elements carbon and hydrogen, and we're giving you 3 equations down here that that we're going to use to find that. All right, so again, what we want to do is we want to look at the reactants and products. So in this equation here, if we call this equation 1, equation 2, equation 3, we can add them in any order. We don't have to go 1, 2, 3, but that's the way I like to do it, just to keep myself organized. So we see here that equation 1 has C2H2 as a reactant, but the reaction we're trying to find delta H for has C2H2 as a product. So what we need to do with equation 1 is flip it to put C2H2 on the product side. This is the only equation where C2H2 appears, so that's what we know we have to do. We have to flip this whole thing to make sure that we have 1 C2H2 on the product side, just like we do in the reaction we're trying to find delta H for. Because again, we're trying to figure out how to add these three equations together to get this given equation up here. So we're going to flip equation 1. And so when we do that, we get reactants and products just swap with each other. So 2CO2 plus H2O, products become reactants, and then the reactants become products. And I'll leave out all the gas symbols and stuff like that. Just look at all we need to really care about is the coefficients for the most part. All right, so we have that, and then because we flip this, delta H is going to be the negative of that first delta H. So it's going to go from minus 1299 to plus 1299.5 kilojoules. All right, so we've modified that. Now we have C2H2 on the product side. If we look at equation 2, equation 2 has carbon as a reactant, and that's the only place that carbon appears in these three equations. The overall reaction has 2 carbons on the reactant side, so we need to double equation 2 to make sure that we have 2 carbons on the reactant side when we combine everything. So we're going to double equation 2, which means we're going to take all these coefficients and double them. So it's going to be 2 carbon plus 2O2 going to 2 CO2. And because we doubled the coefficients, we also have to double the delta H. So we're going to take this value here, which is minus 393.5, and we're going to double it to minus 787. And then finally, we have in equation 3, we have H2 as a reactant, and that's the only place that H2 appears in the 3 given equations down below. H2 is also a reactant in the equation with the unknown delta H, so we're not going to have to do anything to equation 3. We want one H2 on the reactant side, and equation 3 already has one H2 on the reactant side, so we're going to keep that one the same again. We're not going to modify it. So we're going to use equation 3 unmodified. And because we didn't modify it, the delta H is exactly what's given to us. So if we did our job correctly, these 3 equations, 2 of them being modified from what were originally given, should add together to give us 2C plus H2 going to C2H2, and the sum of the 3 modified delta H values will be the overall delta H. So if we look at what's going on here, so in equation 1 we have 2 CO2s as a reactant, but that's going to cancel out with these 2 CO2s that are a product. We have H2O as a reactant in equation 1, but that's going to cancel out with that H2O that's a product in equation 3. And then we have 2C, there's nothing to cancel that with, so that's going to carry forward. We have 2 O2s here on the reactant side, plus 1/2 O2 from equation 3, so that's going to be 2.5 or 5/2 O2 on the reactant side, and we have 5/2 O2 here on the product side. So that O2 that's on the product 5/2 is going to cancel with 2 plus 1/2 O2 from the other 2 equations, which is also a total of 5/2. And then finally, the only reactant that's left is our H2, which doesn't cancel with anything. And then on the product side, the only thing that hasn't so far canceled out is C2H2. All right, so we can verify that these 3 equations add together correctly to give what we're looking for. It's helpful to do this. It's not necessary. I mean, if you trust yourself to arrange these correctly, you could just go straight to adding up the delta H values, but it is helpful to verify that they do add together as they're supposed to. But we verify that, so all that's left is to add the delta H values. We're just going to take these 3 values of delta H and add them together. So it's going to be plus 226.7 kilojoules, assuming I didn't mess anything up with the math. Okay, so we just add the 3 delta H values together after we've modified the equations and modified the delta H values appropriately. So these problems can be a little bit tedious, but it's going to be the same approach every time, just figuring out how to combine the 2 or 3 given equations to make the equation you're trying to find delta H for, and then adding the delta H values once you do that. All right, any questions on this one? Yeah. It cancels out the 2O2 plus the 1/2 O2. So O2 appears in 2 of these equations on the reactant side, so you would combine those as reactants to make 5/2 or 2.5 O2, and then over here you have another 5 halves O2 that it cancels with. So sometimes that happens. You'll have, you know, two pieces. You have to look at, you know, where it appears in all those equations to figure out if it completely cancels or partially cancels, whatever the case may be. All right, anything else? All right, we'll do one last one like that, which is another one with 3 equations. This one ends up being just a little bit more complicated for reasons we'll get into. Now, if you're paying close attention, we're trying to calculate the enthalpy for this reaction, C plus O2 making CO2, so basically forming carbon dioxide for its elements, and that's one of the equations we gave you here, which has this delta H value. So what we'll find is in this last example here, can we combine 3 different equations and get that same delta H value for this reaction, all right? So we have 3 different equations that we're now going to combine. We're going to try to find delta H for that, which should match the delta H from the previous one that I gave you, so if we do everything correctly. Now normally that won't be the case where you'll already know the delta H before you start, but here we do, so we can make sure that it works out. All right, and this is a very roundabout way of finding delta H for this reaction, because we're giving you all these equations that have strontium oxides and strontium carbonates and strontium metal in them, so it's a totally roundabout way of doing it, but we'll see that it does work even though it's kind of convoluted. It's kind of like a Rube Goldberg machine for delta H. Okay, so we have carbon plus oxygen making CO2, so we have to figure out how to combine these. So we want CO2 on the product side, and equation 1, which is the only place where CO2 appears, it's on the reactant side. So we need to flip equation 1 to move CO2 to the product side when we combine the 3. So we're going to flip equation 1, so it's going to be strontium carbonate going to strontium oxide plus CO2. And because we flipped the reaction, we're going to flip the sign of delta H for that first one. Again, we're numbering these as 1, 2, and 3, just to keep them straight from each other. So we're going to flip the sign of delta H1 and make that 234 kilojoules. Now from here, we don't have an obvious place to go because we also need to have O2 and C as a reactant. But if we look at O2 here, O2 appears in 2 of the given equations. So there's a lot, or really an infinite number of ways we can combine equations 2 and 3 to get one O2 on the reactant side. So that's not one we actually want to start with, because again, if one of the reactants or products from this equation here appears more than once in the given equations, we're not going to know how to combine those given equations to get that. There's an infinite number of ways of doing that. So what you want to look for are reactants and products in this overall equation that only appear once in the 3 given equations. So oxygen is not the one to go with now. But if we look at CO2 here, CO2 is already taken care of. But then if we look at carbon, carbon only shows up in equation 3 here. So carbon is a reactant here in the overall equation, and is a product here in equation 3 with a coefficient of 2. So we're going to go a little bit out of order here, but we're going to take equation 3 and we're going to flip it, and we're going to multiply it by 1/2, so that this coefficient of 2 in front of carbon becomes a coefficient of 1, and it moves over to the reaction side. So we're going to go to that one next. There's, again, a lot of different ways you can approach this one, but this is, I think, is the most straightforward way to go to, which is to make sure that we get carbon balanced by moving it to the reaction side and multiplying the coefficients by 1/2. So for equation 3, we're going to flip it and have the coefficient, so it's going to become SR plus C plus 3/2 O2. Then on the product side, it's going to be strontium carbonate. And so that delta H is going to be minus 1/2 times the third delta H value. We flipped it, and we multiplied the coefficients by 1/2, so we're going to change the sign, and we're going to have the value. So it becomes minus 1220 kilojoules. And then from there, we can figure out what we need to do with equation 2, or if we need to use it at all. Now, we do need to use equation 2, because what we'll see is that strontium carbonate, which is an intermediate, it doesn't appear in the overall equation, but it does cancel out, so we're good with that. But we have strontium and we have strontium oxide that are still showing up and not canceling out with any of the other equations. So what we'll see here is that equation 2 has strontium oxide and strontium. It has strontium as a reactant, and we need it to cancel out with this strontium oxide this has strontium oxide as a reactant, and it'll cancel out with that strontium oxide that's on the product side. And then it has 2 strontiums as a product, and we need to cancel out 1 strontium that's a reactant side. So for equation 2, we don't need to flip the direction of it, but we need to multiply it by 1/2. Because if we do that, we'll now have coefficients of 1 in front of strontium oxide and strontium, and those two intermediates will now cancel out with the other two equations where they appear. So we're going to multiply equation 2 by 1/2, and we're going to get strontium oxide going to strontium and 1/2 O2. And so now we have SRO canceling out, left of the arrow here, right of the arrow there. SR cancels out, right of the arrow here, left of the arrow there. So we need to make sure intermediates cancel out as well. So this one we had to actually use the intermediates to help us figure out how to balance that last equation. And so the delta H for this is going to be just 1/2 times the second delta H, which is going to be 1184 times 1/2, which is 592. And now we're ready to add everything together, see if the overall equation works out, and then get the delta H value. So when we add these together, from the first equation we have strontium carbonate as a reactant, but it cancels out with that strontium carbonate that's on the right side of the arrow. From the second equation we have strontium SR as a reactant, but it's going to cancel out with that SR that's on the product side. But we have carbon here, which does not cancel out, nor should it, so we're going to have carbon carrying through as a reactant. And then let's do oxygen last because it's a little bit more tricky in this case. And then we have SRO here as a reactant canceling out over there. But we have to figure out how oxygen works out because oxygen appears in two places here. So we have 3/2 O2 on the reactant side up here, but we have 1/2 O2 on the product side in the third equation. So those are going to partially cancel out. They don't have the same coefficients, so they don't completely, but we have 3/2 O2 on one side of the arrow. Let me just write that out in partial form. We have 1/2 O2 on the product side from this equation here. So if we subtract 1/2 O2 from each side, we're left with 1 O2 on the reactant side. So in net, we have 1 O2 on the reactant side, which is what we want. All right, so in this case, O2 partially canceled out. It was 3/2 from this equation, 1/2 from this equation on the other side. So you subtract 1/2 O2 from each side and left with 1 O2. So O2 takes care of itself as well. That one partially cancels out, and that coefficient goes from 3/2 to 1, but it's not completely canceled. And then finally on the product side, all that's left is CO2. All right, so we can verify that those three add together. And the delta H's are now just going to add up. So we have 234 kilojoules plus minus 1220 kilojoules plus 592 kilojoules comes out to minus 394 kilojoules, and that matches the delta H that was given to us as part of the previous problem for the same equation, carbon plus oxygen making CO2. So the math and the numbers all check out. All right, so that one was a little bit more complicated because, again, O2 appeared in two different equations, so it was a little bit harder to figure out how to combine the equations to make sure that we were left with 1 O2 on the reactant side and to make sure that all intermediates canceled out, which is what we ended up going with. All right, so any questions on that process? It's going to take some practice, obviously, but it's, again, the same approach every time, so just learn the approach and get used to, get comfortable with doing it. Now what we're going to move into now is a more practical way of finding delta H for unknown equations, because as you saw in that last one, it can get kind of hairy when you're combining three equations, especially when those three equations don't really seem to have anything to do with the reaction you're interested in. So that's not really the most, elegant or straightforward way of doing it. But the way that it's going to be done more commonly, at least in real life, maybe not necessarily in this course, but in real life it's a lot more common, is to use what are called formation equations to then be able to find delta H for any unknown chemical reaction that we're trying to study. Again, this allows us to calculate delta H for a reaction without having to go in the lab and measure it and do the calorimetry experiments and all that stuff. All right, so first we have to define what a formation equation is, because these are the types of equations that we're now going to learn how to combine to be able to determine delta H for any chemical equation that we really want. So a formation equation is a chemical equation, and what it shows is the formation of 1 mole of a compound. And so that's important. The product side has 1 mole of a compound. And it's going to form from elements in their standard state. So we'll have to define a little bit what it means to be in the standard states in a little bit. But this is what a formation equation shows. It shows the formation of a compound from its elements. all right? So it's okay to have fractional coefficients on the reactant side. Sometimes you will have that, as we'll see. There's always going to be a coefficient of 1 on the product side for whatever compound is being formed in this formation equation. And so the general form of a formation equation in the most generic terms is going to be elements on the left side of the arrow forming 1 mole of compound on the right side with a coefficient of 1, or in reality no coefficient, given implied as 1. So that's what every formation equation is going to look like. Elements as reactants forming some compound as the product. So that's what a formation equation is. So let's just talk a little bit more about that. So as we said, formation equations involve forming a compound from elements in their standard state. So what does it mean to be in the standard, what does the standard state of an element mean? Basically, it's the form of the element that exists at sort of, normal temperature, normal pressure that we have here on Earth. So, if you were to dig up a sample of an element from somewhere in the world, this is the form that it would be in as a pure element. So the standard state involves both the state of matter for that element, gases, liquids, and solids, as well as sort of the molecular or atomic form that element takes in its standard state as well. So we'll talk about both of those. So there's a few elements that are gases. We need to remember which ones those are. So obviously the noble gases exist as gases. And those are going to be, just as we said before, just monoatomic elements. So neon will just be Ne. Krypton will just be Kr. They don't form bonds with each other for reasons we learned in chapter 4, and they are all gases at room temperature and regular pressures. Now there's some other non-metal elements that exist as gases as well. So that's going to be hydrogen, and the rest of these are all diatomic. So these other non-metals that exist as gases all exist as diatomic gases in their standard state, meaning they're going to be consisting of molecules where 2 of those atoms are bonded together. So hydrogen, which is H2, nitrogen, which is N2, oxygen, which is O2, fluorine and chlorine, 2 of the lighter halogens, all appear as gases. All of them are diatomic. All right, and so again, nitrogen, oxygen, N2, and O2, that makes up 99% of our atmosphere, and that's the form that they would be in the air that you breathe. And then there's only 2 elements on the whole periodic table, believe it or not, out of the 118 or so that there are. There's only 2 elements that are liquids at standard state, which is kind of weird to think about, but that's certainly true. So the only liquids are, if we go down the halogen column to bromine, that ends up being a liquid. Some of these standard states will make a little bit more sense once we get through chapter 9. So at the end of the course, this will start to be a little more intuitive instead of just seeming like a random list. But nonetheless, as we go to bromine, it exists as a liquid. And then there's one metal on the periodic table that exists as a liquid. Does anybody know what it is? Yes, mercury. So it's fun to play with, although I wouldn't recommend it too much because it is kind of toxic as well. Liquid mercury is not as scary as people think it is, but I still wouldn't recommend drinking it or anything. But it is a liquid. That's the only metal in its pure form that exists as a liquid. And then everything else on the periodic table, so except for the noble gas column, except for these 5 nonmetals, and then these 2 here that are liquids, everything else is a solid in its standard state. And so that's going to be true for all the metals on the periodic table except for mercury, and all the metals are just monoatomic. So there's no bonding between them. You don't form like molecules of metal. So it'll just be Na for sodium, or Fe for iron, or K for potassium, and they're all going to be solids at room temperature. But there are a few solids that are also still polyatomic, meaning that they have 2 or more atoms bonded together in their standard state. So the polyatomic solids are all nonmetals, and they're going to be the heaviest halogen, I2, which is a solid, iodine, and then phosphorus exists as P4, sulfur as S8, and then selenium, which is right below it, as Se8. So you do have to kind of remember that these ones are, so most of the nonmetals exist as polyatomic forms, either diatomic, as we have here, or in some cases higher order molecules where you have 4 phosphorus atoms, or 8 sulfur atoms, or 8 selenium atoms bonded together. So those are the standard states for all the elements. So you have to be able to recognize those when we're dealing with formation equations. But it's not too bad once you internalize all of that. And then from there, once we have a formation equation, then the enthalpy change associated with that will be called the standard enthalpy of formation. So the standard enthalpy of formation is the enthalpy change associated with a formation equation. All right, so again, a thermochemical equation is one that has a balanced chemical equation with an associated delta H. And so these formation equations can be written as thermochemical equations where the enthalpy change is called the enthalpy of formation. And there's another term that you'll often see for this. It's often called the heat of formation, which is not the most precise terminology, but we do know that heat and enthalpy are related to each other, so that's a term that's used sometimes. And it's going to be abbreviated as delta H with a little 0 indicating standard states. That'll be defined more clearly in Chem 2 if you go to that, and then a little F indicating that's a formation enthalpy. So when you see delta HF with a little degree sign or 0 next to it, that means standard enthalpy of formation, the enthalpy change associated with forming a compound from elements in their standard states. Now there's going to be approximately 100 and some substances in the world where you would already know the delta H of formation without even being told what it is. So normally in these problems that we're going to do, we're going to give you delta H of formation for a lot of the substances that are involved, but there's going to be 100 and some substances where the delta H of formation is already known. And so to think about what that would be, what is the standard state of enthalpy what is the standard enthalpy of formation for an element in its standard state? Is it going to be 0, is it going to be positive, is it going to be negative, or does it depend on the element? Any guesses? All right, someone said 0, and I like that answer. So any element in its standard state, all the ones that I told you about before, where every element has a specific standard state, the enthalpy of formation for that element is 0. And that's because, let's say we take hydrogen. Remember, the enthalpy of formation is going to be forming 1 mole of that substance from the elements in their standard state. So if we're forming an element from elements, there's no change, there's no net reaction, and so the enthalpy change is 0. So when you're doing problems that involve formation enthalpies, if you see an element in the problem, you already know without having to look it up or being told that the enthalpy of formation for the element is 0. That's true for every element on the periodic table if it's in its standard state. So elements in their standard states have enthalpy of formation of 0, but any other compound that would form from elements is going to have a non-zero delta H formation. It can be positive or negative. Negative is more common, but there's certainly both. And again, it depends on the substance that's involved, the strength of the bonds that form. All those things are all important. All right, so let's do a few examples of just problems dealing with formation, or just I guess one example here. So this is sodium carbonate, that's what it looks like. And we're gonna know which of the following represents a formation equation, specifically the formation equation for sodium carbonate. So if we're doing a problem like this where we're asking to identify a formation equation, remember that there's 2 key things here. There should only be elements on the reactant side. And those have to be in their standard states. And there should only be 1 mole of whatever compound there is as a product. So again, those are the 2 key features of a formation equation. Standard states elements as reactants, and 1 mole of compound as a product. So if we look at choice A here, it does have 1 mole of compound as the product, but the reactants are not elements. So this one is not a formation equation because the reactants are not elements. If we look at choice B here, we're forming 1 mole of a compound, so that looks good. And then if we look at the reactant side, they're all elements. Sodium solid, so that's going to be the standard state for pretty much every metal. Carbon is the standard state for carbon, which is a form of carbon called graphite, which is labeled as C. And then O2 gas, that's the standard state for oxygen. So this one looks pretty good because it's balanced. It does have a fractional coefficient, as we said, is sometimes necessary, but it's 1 mole of compound forming from elements in their standard states. That one looks good to us. Let's check the other 2 and find out why they're not formation equations. So choice C here is just doubling answer choice B, but remember that we don't want to have any coefficients on the product side. So this here has a coefficient of 2 in front of the product. Formation equations only involve forming 1 mole of product, so that one's going to be not a formation equation. It is balanced without any fractions, but remember we always want to balance it with only a coefficient of 1 on the product side. So that one's going to be not a standard formation equation. And then finally for this last one here, we're forming 1 mole of a compound, so that looks good. And it looks at first glance, it looks like we have all elements on the reactant side. We have sodium, we have carbon, we have O, but remember that the standard state for oxygen is not just O, it's O2. So this would not be oxygen in a standard state, so this would not represent a formation equation because the reactant, in this case, the oxygen that's on the reactant side, is not a standard state element. Oxygen has to be as O2, and O2 gas in particular, if we're talking about oxygen in its standard state. So all the rest of those are not formation equations for various reasons, but choice B is correctly written as a formation equation, 1 mole of compound forming from elements. All right, and then what we're going to use these for then is we're going to be able to find delta H for any reaction when we know the delta H of formation for each reactant and product. So this is essentially an application of Hess's law. What you're really doing here is you're taking all the formation equations for reactants and products, you're adjusting the coefficients, flipping some of them, and then combining them like we did before. But if you're dealing with formation equations, you don't necessarily have to write out all the equations. There's just going to be a standard mathematical equation we use to find delta H when we know all the delta H formation values. And so it saves a lot of time in this case because you don't have to go through and figure out how to adjust coefficients, figure out which ones you have to flip, which ones you don't, add them together. All that stuff is sort of washes out if we're using exclusively formation equations to do this. So the delta H for a reaction is going to be the sum of the delta H's of formation on the product side. So it's going to be products minus reactants. So in order to do this, we need to know delta H of formation for the reactants and the products. And when we know those values, we just sum them up on the product side, sum them up on the reactant side, and subtract the two. So again, this Greek letter here means sigma, which means to sum them up, which I think we've seen before in some other context. So you're summing up the delta H of formation on each side, and then these coefficients here, m and n, those are the coefficients for each reactant and product. Because remember that a formation equation refers to the formation of 1 mole of that substance, and so if there's a coefficient that's not 1 in the balanced equation, you have to multiply the delta H of formation by that to account for the fact that you have something other than 1 mole of that substance involved in the equation. And as we said already, any elements that are involved have a delta H of formation of 0, so they basically would drop out of this. All right, but for any other reactant or product that's not an element, you would need to know what the delta H formation values are. You multiply them by the coefficients, add the products, and subtract. I forgot to do the lysae. It looks like it's going to do it for me anyway. All right, so let's just use this in a couple of examples and see how this works. So we have here the combustion of methane, which is CH4 plus 2O2 going to CO2 and water. And we just want to know the delta H for this reaction. So what is the delta H for this? RxN is an abbreviation for reaction, if that wasn't obvious. So we're trying to find the delta H for this reaction. Technically at standard states we put a little 0 there, but that's not terribly important for how we do this. So the delta H for reaction, as we said, is just going to be the sum of the delta H's of formation for the products minus the sum for the reactants, where we have to multiply each one by the appropriate coefficients.
What does that stand for, like RC? Is that RC or like the delta H something?
RxN,
RC?
that stands for reaction.
Oh, okay.
All right, so we're going to have products minus reactants, and we just have to put in the numbers. All right, so on the product side, we have 1 CO2. So we're going to use that delta H of formation multiplied by 1. And then we also have 2 water, so we're going to take 2 times the delta H of formation of water. So that's the product side, and then we're going to subtract from that. On the reactant side, we have 1 CH4 and 2 O2. So 2 times the delta H of formation of O2. But again, we weren't given the delta H of formation for O2. We have it for CH4, we have it for CO2, we have it for water. O2, though, is an element in its standard state. It's O2 gas, so this term goes to 0. So that'll basically drop out, and what's left then are the rest of them. So on the product side, we have 1 CO2, and the delta H formation for CO2 is minus 393.5. And then we have 2 moles of water, and the delta H formation for water is given as minus 241.8. And then we're going to subtract from that 1 CH4 on the reactant side, which has a delta H formation of minus 74.9. So usually the only thing that people mess up here is signs. You have to remember that we're subtracting what's on the reactant side, so we're subtracting a negative number, which is the same as adding it. And so what's left mathematically is minus 802.2 kilojoules. So that's going to be the delta H for the combustion of 1 mole of CH4. Again, it releases a lot of energy whenever we burn a hydrocarbon substance. Okay, so that's the equation, just products minus reactants. Make sure we multiply each one by the correct coefficient to be able to do that. So any questions on that? Yeah, Kyle?
Why the oxygen cancel out like the?
Because oxygen is an element in its standard state, and so any element in its standard state will have a delta H formation of 0.
Oh,
So that one we don't have to worry about. It'll just drop out.
right.
Anything else? All right, we'll just do one more example like that before we wrap up today. So we have this reaction here. So this is what's called red phosphorus. This is not the standard state of phosphorus. So some elements have more than one form that they can exist in. So the standard state for phosphorus is P4, but there's another form called red phosphorus that looks like this. It is, of course, red as the name suggests. And red phosphorus reacts with nitric acid and water to make phosphoric acid and release NO2 gas. We want to find the delta H for this reaction. So this one's a little bit more complicated because it has more reactants and products. And the only thing we have to be careful about here is that we have red phosphorus. So in this case, this is not an element in its standard state, so its delta H formation is not 0. It's given here as minus 17.6. So it is an element, it is still phosphorus, but it's not a standard state element, so its delta H formation is non-zero. So you have to make sure we still use it, because it's not a standard state element. All right, but then from there we can just go and use the same equation that we did last time. So delta H for the reaction is going to be products minus reactants. So it's going to be 1 times the delta H of formation of H2O. So H2O is the first product, and that's going to be minus 285.84. You'll notice that that value is a little bit different than the last one because this case is H2O liquid. The last one was H2O gas. So the state of the substance depends on or determines the delta H as well. The next product is H3PO4. It has a coefficient of 1 as well. So it's going to be 1 times the delta H formation for H3PO4, which is minus, come on. It's telling us that class is supposed to be over. We have 3 minutes left. Give me a break. All right. All right, so we have minus 1271.7 for H3PO4. That's the second product. And then the last product is NO2, which has a delta H formation of positive 33.2. So we're going to have to multiply that by 5, though, because there's a coefficient of 5 in front of NO2. So that's the product side, and then we're going to subtract from that the delta H is a formation on reactants. So on the reactant side, we have phosphorus and HNO3. Phosphorus, as we said in this case, is in a non-standard state, so its delta H will not be 0. So there's a coefficient of 1 for that, but it has a delta H of minus 17.6. If it was P4, it would be 0, but here it's red phosphorus, which is non-zero because it's not a standard state. And then the other reactant that we have is HNO3. There's a coefficient of 5 in front of that, so we have to multiply that value by 5. HNO3 is minus 173.33. And so that's going to be, again, products minus reactants. So you have to make sure we do the math correctly. And if I didn't screw anything up, looks like we got all the numbers correct, I believe. It's going to be minus 507.29 kilojoules, which if in a multiple choice question would be choice C. All right, so as I said in problems like this, messing up the signs is probably the most common mistake people make. So choice A would be one that you would get if you flipped, if you did reactants minus products instead of products minus reactants. But other than that, you just have to remember the coefficients and just don't mess up any signs and you're good to go. All right, so any last questions before I wrap up? All right, I will be in my office most of the time until 2:30 if you need to come see me with any last minute questions on your exam. So I'll be there for most of the next 3 hours. I think there'll be about 30 minutes or so that I'll be out, but So,
During your office hours, did
but I'll see you.
advance on your exam?
If you want to talk to me about your exam you've already taken, I would prefer if you wait till Thursday after the results are open up to everybody. But yeah, anytime Thursday or after, we can talk about exam results as well.
I didn't get